Hello and welcome back to High Peak Education. In this video, I would like to discuss rotational motion for a calculus-based Physics 1 class. Namely, I would like to discuss rotational kinematics. I would also like to discuss rotational mass, which we know to be moment of inertia, sometimes called rotational inertia. And I would like to discuss more things related to rotation itself. Now, this will lead us into chapters where we make analogies for everything we've learned this semester so far for linear motion and for conservation laws and for forces, but we will make those analogies soon for rotation. By the way, a lot of these things, especially rotational kinematics, can pertain directly to a particle, but in general, once we start discussing rotational inertia, the object has substantial mass and it's rotating as a solid body. And so we will look at that for an extended object that has a rotation axis somewhere through the object. So let's begin. So first I want to discuss what is uniform circular motion. Let's make sure that definition is carefully crafted. It's rotational motion at a constant rate of rotation. Okay? So that means a constant angular speed and also a constant linear or tangential velocity as long as the radius is constant. Now I want to introduce an important concept, namely counterclockwise versus clockwise. Counterclockwise we call positive rotation, and clockwise we call negative. By the way, for those of you over in Europe, counterclockwise you know as anti-clockwise. Well, the reason for that is because of the so-called right-hand corkscrew rule. That is to say, if the positive x-axis is this way and the positive y-axis is that way, by x pushed into y, the positive z-axis, or the direction of the axis of rotation, would be in the positive direction as long as the rotation is counterclockwise. Now, I'm hoping many of you watching this video, if you've taken a trigonometry class and things before, your professor defined positive angle displacement as counterclockwise. And in previous videos, I've done that. So this is the convention I will use throughout the semester unless for some reason otherwise specified. But 99% of the world uses the right-hand rule, a right-handed positive coordinate system. Now the angular speed, and by the way, angular speed becomes angular velocity if we take into account positive versus negative, counterclockwise versus clockwise. The angular speed is constant in uniform circular motion. Now the tangential speed is the radial distance times the rotational speed. So v tangential is omega times r. This is sometimes called the linear speed. Note the dependence, of tangential speed on the radius. Okay? So you'll note that this ladybug is moving fast on this record player, but this ladybug on the outer edge is moving twice as fast. Now the idea is that the reason this is moving twice as fast is because it has twice the tangential speed. It moves at twice as large of a circumference as this one does in the same amount of time. But they both have the same omega. That is, they both have the same angular speed. So their rate of rotation, their number of radians per second, or the more common units would be revolutions per second for angular speed or angular velocity, that is the same for both of them because they're both on a turntable in solid body rotation. So let's also discuss period, the word and the concept for period in uniform circular motion. The time interval to complete one revolution is called the period capital T. The period capital T is related to the linear speed v, as v equals 1 circumference divided by 1 period. So 2 pi r divided by t should be v. So we can solve for t by saying 2 pi r over v is t. So time is distance, that's curved distance because it's a circumference, divided by speed. And that seems entirely reasonable if you're along the tangent edge here. Okay? Notice that the circumference is a curved arc length S for an entire circle. So S could be some portion of this circle, but it's a curved arc length distance. And then notice that, by the way, the velocity, that is the linear or the tangential velocity, is always tangent to the circle. And the velocity vectors in uniform circular motion are all the same length. That is, they're all the same magnitude. Notice the velocity vectors are also perpendicular to these radii. Finally, from the angular perspective, we know that if period is 2 pi r over v, we now know from the previous slide v equals omega times r. So the r's would cancel, so you get 2 pi over omega is t. So period is 2 pi radians over omega in radians per second. But that should hopefully make sense to you. We asked the question, how fast do we rotate through radian space? Well, 2 pi radians is 1 revolution divided by omega in radians per second gives the time in seconds. Now, how do we define solid body rotation? How do we define these rotational kinematic variables? So notice that when we're in solid body rotation, this reference line rotates such that we have a point moving along a curved arc S. The radius stays constant, and theta is an angular change. So all points move with the same delta theta. Now the rotation angle, delta theta, is going to equal S over R, where S is the arc length. Hopefully you learned that formula somewhere in your life, maybe like a trigonometry or a pre-calculus class, that S is in meters, R is in meters, so delta theta is in radians. And radians are really unitless. So what we'll see here is we know that S for 1 revolution through 1 full arc length of 1 circular path is 2 pi r. That's the circumference. So the rotation angle for 1 revolution is just going to be delta theta equals 2 pi. So we're going to make a definition. We're going to say that 2 pi radians is defined as 1 revolution, and radians will be the SI unit of angle. Now, by the way, previously in this class, we've mostly used degrees. But it turns out that degrees are only if you really have a reference line. Here's our reference line, but it's easier when we talk about rotations to just use radians because you don't necessarily have to choose a reference line of any particular point. You just want to know how many times has the actual solid body rotated through. By the way, notice that 2 pi radians is 1 revolution. Sometimes people write pi radians as 180 degrees because 2 pi radians is 360 degrees. So notice that if you divide by 2 pi, which is about 6.28, 1 radian is about 57.3 degrees. You don't really need to know that fact, but I'm just mentioning to you right here is approximately 1 radian, about 57.3 degrees. By the way, again, radians are unitless. It's good to keep radians around if you're referring to a rotational quantity. But as soon as radians are multiplied by a linear quantity, like meters, we intentionally sweep radians under the rug. Radians are in some sense a counting unit because in 1 full revolution, the total displacement is 0. So let that sink in for a second. If the total displacement is 0, in some sense, radians just count things. They don't really have a unit like a length like we saw earlier in the semester. So let's talk about angular speed, its relationship to tangential speed, and angular acceleration. Okay? Define the average angular speed. That's going to be delta theta over delta t, because that's going to be omega, the average angular speed. By the way, if this is positive versus negative, that makes it an angular velocity. So it's the change in angle divided by the change in time. The units will be radians per second, because again, that's all SI units. Angular speed in terms of linear or tangential speed is going to be units of meters per second, and that's units of radians per second times meters. So that's going to be V equals omega times R. Notice that the radians intentionally get swept under the rug. In some sense, it's unitless and sort of goes away when we go from angular velocity to linear velocity. Now, by the way, to talk about a linear velocity, we have to choose a specific radius. So omega can either be clockwise, meaning it's negative. So like this record here, this vinyl record is moving clockwise, so this omega is negative. Or it can be counterclockwise, so omega is positive. The tangential velocity is always tangent to the path. When the angular speed does change, though, the rotating object experiences an average angular acceleration. So what happens when you first turn on the record player? This thing starts to spin, but then faster and faster and faster and faster and faster. So the idea is that it's angularly accelerating. We define angular acceleration as the symbol lowercase Greek letter alpha, and the definition is delta omega over delta t, the change in the angle over the change in time. Now, by the way, delta omega is in radians per second, and then delta t is in seconds, so alpha should be in units of radians per second squared. Okay, I hope all those definitions really make sense. By the way, I've already alluded to the right-hand rule. Notice that if I look at a turntable that, as viewed from above, is rotating counterclockwise, that would be a positive sense of rotation. My thumb would point upward from the axis of rotation out from the turntable. If the turntable is rotating clockwise, my thumb points into the page, that would be negative. Now, by the way, many of you actually probably learned this before with the old righty-tighty, lefty-loosey, when you have threads on, say, a screw. Well, righty-tighty is negative because the screw goes down into the object, but lefty-loosey, the screw comes up at you, that's positive, and that's counterclockwise, the way you turn a screw. So hopefully that makes sense. Let's talk a little bit more about the mathematics, and in particular the calculus, to go from some t initial to t final, some point A to some point B, some theta initial to theta final. Let's keep the radius constant, and let's let there be a rate of rotation. So angular displacement is change in theta, so that's theta final minus theta initial. Average angular speed is delta theta over delta t, units of radians per second. If you want the instantaneous angular speed, the angular speed at any moment, we have to use calculus by allowing the time interval to shrink to 0. In other words, we take the limit as delta t approaches 0, and we get the time derivative, namely d theta dt is omega. So angular velocity is the instantaneous rate of change of theta with respect to time. How about define the average and the instantaneous angular acceleration? We do it in the same sort of way. The average angular acceleration, again, the object is sort of speeding up its rate of rotation. Alpha average is delta omega over delta t. And if you use calculus, and we're going to use Leibniz's notation again, we take the limit as delta t approaches 0. The change in omega over change in time is d omega dt, the change of the angular velocity with respect to time at any moment, because again, this is instantaneous. Now, what is rotational kinematics? Very similar to chapters 2 and 3 of this course, kinematics deals with describing motion only. In other words, how things move, with no consideration of mass or forces. In other words, we want to know how fast, how far, how long, how much did it accelerate, things like that. For linear motion, if you recall, we derived equations of motion at constant acceleration in terms of v initial, v final, delta x, t, and ax. That is, initial and final velocity, displacement, time, and acceleration. And we assumed the acceleration was constant. So that was just a constant number. We can do the same thing for rotational quantities if they are omega initial, omega final, delta theta, t, and alpha. That is angular velocity initial, angular velocity final, angular displacement, time, and angular acceleration. By the way, sometimes people call this rotational velocity, rotational displacement, and rotational acceleration. Really just means the exact same thing. So let's look at our kinematic equations one at a time. Notice that here we have the definition of acceleration, but now for rotation. Here we have the displacement curve, but now for rotation. Here we have the square of the velocities equation for rotation, and using the definition, the fact that the angular acceleration is a constant number, here is the average angular velocity, that's omega initial plus omega final over 2. Why can we do that? Because for each segment, if we're constantly speeding up or constantly slowing down, the average omega over that time interval will just be the linear average, the 2-point average of the initial and the final angular velocities. So then the other equation is the displacement is average angular velocity times time. Remember, the definition of acceleration ignores delta theta, the angular displacement. The displacement curve ignores omega final, that is the final angular velocity. The square of velocities equation ignores time. And then the displacement average angular velocity equation ignores acceleration. Again, these have the exact same form as their linear companions. And here's my recommendation as before in terms of an algorithm. Follow the same rules. List out the 5 kinematic variables. If you have 3 variables, you can solve for the 4th, and the equation choice is based upon the ignored variable. So let's just say I have omega initial, I have delta theta, I'm looking for t, and I have alpha. I would choose the displacement curve. Why is that? Because if I'm looking for time, but I don't have the final angular velocity, I don't care about the final angular velocity, and I don't need to solve for it. So that suggests the displacement curve. There's no omega final. Furthermore, t can be solved for because the rest of the values are known. Now, by the way, in that special case, you would actually need to use the quadratic formula because t is in more than one term. But you all are smart and know how to use the quadratic formula. You could also use factoring or a piece of software. Or, by the way, there's lots of great videos out there. I do want to briefly refer to Grant Sanderson and 3 Blue 1 Brown. He's got an excellent new video about an alternative way to do the quadratic formula or solve quadratic equations. I'd recommend you check that out. Okay, so let us proceed. So here's how the rotational kinematics look just like the linear kinematics. Notice there's exact analogies between these equations. By the way, this comes from one of my previous textbooks. So delta theta is written out like so, and so is delta x. And notice that the average velocity is written out, again, 1/2 the sum of those two velocities, whether it's linear or angular. And everything else pretty much looks the same. Here's an example of a car doing a panic stop, but I will perform this example in a later video. So let's define the difference between centripetal and tangential acceleration. Now, first of all, angular acceleration, not to muddy the waters here, but angular acceleration is something we discussed a few minutes ago. That's a rotational variable. That's in radians per second squared. That's how quickly things start to rotate faster. That's not a linear variable, but it's related to this discussion. So let us compare and contrast centripetal acceleration versus tangential acceleration. Consider a particle here on a large turntable, and it's moving in a circular path, but it's also speeding up. Okay? So what's its difference between its centripetal and its tangential acceleration? Well, the point is that centripetal acceleration points toward the center of the circle. It affects direction. It holds things in circular motion. Whether an object's in uniform circular motion or not, whether it's speeding up its rate of rotation or not, it must have centripetal acceleration because it's directionally accelerating. We know that from chapter 4. It must be held in circular motion toward the center of the circle. That's the so-called radial acceleration. But what that means is if centripetal acceleration is v squared divided by r, linear velocity squared divided by radius, we know that v is equal to omega times r from a previous slide. So if we insert that in, we get omega squared times r because one of the r's cancels. So notice a larger rotation rate, a larger angle omega, will give you a larger centripetal acceleration. That seems very similar to this with the linear velocity. But look, by contrast, a larger radius means a larger centripetal acceleration. Whereas here, a larger radius means a smaller centripetal acceleration. Now you may ask, why does that seem to be different or opposite? I recommend using v squared over r when you're talking about a single particle. Because with a single particle, usually with, say, a car going around a turn, we focus only on the linear velocity of the car, not the angular velocity. And we talk about curves of different radii. But here, with omega squared times r, we focus on different objects usually on the same turntable or on the same object that's in solid body rotation. Since they all have the same angular velocity, the ones at a larger radius will require a larger centripetal acceleration to be held in circular motion. Now remember, like I said a moment ago, the angular acceleration speeds up or slows down the rate of rotation. As a result, let's define the tangential acceleration. The tangential acceleration is going to have units of meters per second squared, and that's going to be the angular acceleration, radians per second squared, times the radius in meters. So that's alpha times r is at. Notice at is what's going to speed up or slow down the linear velocity. So that's why at is in units of meters per second squared. Notice at, the tangential acceleration, will always be perpendicular to AC, the centripetal acceleration. That is, the tangential and the radial accelerations will always be orthogonal. So here's another example of rotational motion coupled with linear motion. So I will do this in a different video. So in fact, I'd like to end this video right here. I will pick up with rotational kinetic energy in a different YouTube video. If you like this content, please smash that like button and give it a thumbs up and let me know that you enjoyed it. Please subscribe to the channel to grow the channel. Please share it amongst your social network. And I want to thank you for watching High Peak Education. I will see you in the next video.